So I'm talking this morning about when personal and professional worlds collide. So professionally, I'm trained as a molecular neurobiologist. My personal part of this is my wife, Raylan Burke, whom I've been married to for 25 years or more. She was one of the pioneers in the biotech industry in the Bay Area. She was actually employee number 6 at Chiron that was acquired by Novartis. She worked mainly on vaccine development when she was in Chiron. And that meant when Elan was developing its drug to try and treat amyloid plaques in brain, to try and develop an immune response, amyloid plaques, Raylan was hired as being their consultant. Then, unfortunately, about 10 years ago, she developed in her mid-50s early onset Alzheimer's disease. Right? So very quickly, she lost her driver's license. She lost her job at SRI International. And while she could do it, she was still an advocate for Alzheimer's Association. She was an attractive candidate because she actually enrolled in the clinical trial, which was testing the drug that she was developing. Of course, that trial failed. Well, where the sort of collision comes in for me is that I'm a molecular neurologist. I'm supposed to understand what's going on in proteins in the brain, and I was watching my wife deteriorate very, very quickly. So what do I do about this? So one of the things I decided to do is to step back and look at the bigger picture. I gave up my own research lab to try and look and see what can one do to try and address that. And I have to say, when you turn around and look at the disease, not as a researcher trying to get research grants from NIH, but as someone who's is a caregiver and watching someone deteriorate in front of your eyes, you actually look at the whole system very differently. And so what was very quickly apparent to me is that this was 5 years ago now when I started this, and looking at it, you have to look at it somewhat differently. 5 years ago, everyone was all enthused about amyloid plaques and causing cognitive loss in the brain. There was very little evidence for that. There still is very little evidence for it. We know taking away amyloid plaque from humans doesn't seem to do much for cognition, even yet. But this was not only the major research theme in Alzheimer's. It actually, it was the people who were running it were almost suppressing the development of alternative ideas because it became a sort of an established hierarchy. Now, they justified their conclusions on they could cure mice of Alzheimer's. Now, there's 120 different mouse models of Alzheimer's, right? And of course, they're all created on the assumption that amyloid plaques are causing Alzheimer's. So it's a little bit circular reasoning, and I think we'd have to admit that it's unlikely that all 120 mouse models are going to be valid. They can't all be correct, right? So this whole massive field was great, and it may still produce great things, but it seemed one had to think about this differently. Now, so I work in a medical school. I am used to seeing clinical data. And it seemed to me if you want to deal with a human disease and the mouse data are not looking very impressive, what can you learn by looking at the clinical aspects? Now, there's no clinical thing that cures Alzheimer's, but can you turn it around and say, well, look at what accelerates Alzheimer's to maybe get a different approach to the whole thing? So that's what we did, right? And it's quite surprising. Every caregiver, including the caregivers who look after my wife, know that if a person with Alzheimer's gets a urinary tract infection or a chest infection, their cognitive powers go down the tube, right? It's quite well known. Surgery. Surgeons do not like to do surgery on Alzheimer's patients because they know after surgery, there's often a major acceleration of the cognitive loss. Falls. When you look in our geriatric clinic, most of the people coming in now with cognitive loss, a lot of them have had falls. Trauma to the brain is accelerating the Alzheimer's phenotype. And finally, when people come in with brain tumors in Alzheimer's, you don't want to give them radiation because that also accelerates cognitive loss, right? So this is coming out of the clinical literature. So now you ask, what are those 4 things? How do they all come about? Well, when you look at them, you find that there's an incredible range of medical problems coming up associated with these 4 accelerators. You get monocyte migration into the brain, you get obesity effects, you get stem cells coming in, you get vascular things. So I have to say, you sort of get a headache when you try to think about how you can integrate all this information into a useful story. So this led us to think about, well, what is wrong with academia right now? Something that very few academics actually want to discuss. We want to stay, as someone said, it's like a cross between the Vatican and the British monarchy. And one of the major problems, because of our National Institute funding, because of the funding mechanisms, because of our certification projects, because of our promotion things, we all tend to work in silos. That's very well known. Trying to change that silos system is not going to work, certainly in my lifetime, right? It's very much embedded in the system. So what one has to do is to come up with some way of networking these silos together, a simple networking thing. So that's what I tried to do. And the idea here was to, because I have a physics background, to think more or less in terms of breadboards. Now, for those of you who you've probably bought these for your kids. You can actually take a breadboard with all sorts of circuit elements on it, transistors, resistors, capacitors, and so on. And what output you get from a breadboard depends on how you connect things together. You can get out all sorts of different things as long as you have a plan for connection. That seemed to me as being an incredible metaphor. It's not the one I wanted. A metaphor for how universities work. They have all of these components, and you can get all sorts of outputs depending on how you connect them. So someone's working on sterile immunity, that can be involved in wound repair, but it can be involved in cognitive loss. It can be involved in all sorts of things. So we can wire them people together differently. Now, I had the chance to see if this idea worked because we developed a partnership with Calico. Calico is a spin-off from Google with Larry Page. Some of you may have seen this very dramatic Time magazine cover some time back. But anyway, QB3, the institution I run, and Calico made an agreement to try and work together on a longevity institute. We sort of think of this, here we're not going to put up a building, we're not going to go and find directors, we're going to have a pop-up institute. We're going to take what we have, connect them together in a breadboard thing, and see if this would work. So the circuit that we came up with is shown on this slide here, which is pretty complicated. Each one of those little boxes corresponds to a faculty member or faculty members in the QB3 domain. Very complicated, I won't go through it. Let me just show you, does it actually work? And so I'm going to spend a few minutes discussing a little bit of science, so bear with me on that. I'll keep it simple. We have, we think, 4 new ways of approaching cognitive loss and aging, right? Quite different, quite unusual. The first one is, what you find when you get obesity or trauma or surgery on the limbs, you find actually bone marrow monocytes move into the brain. Right? So if you get, say, brain damage, TBI, these things move from the bone marrow through the blood-brain barrier into your brain. When they get there, you think that might be a good thing, but in fact, it seems to cause more harm than good. Why that is so, we don't know. However, if you block that migration of things from the bone into the brain, with which you can do by inhibiting the CCL2 receptor, you find you do not get as much cognitive loss. Right? And that's true when you do look at radiation, surgery, or traumatic brain injury. Another thing, second point, we have in our brain these microglia, which actually use to tune up our synapses in the brain. They're really surprising. You can actually deplete the brain of these microglia, take away 95% of them, and you can't see any difference in the animal. It's really amazing. You would be surprised at that. It goes away. And you can do this using this drug which inhibits it's from Plexicon, that inhibits the CSF1 receptor. So it has no phenotype, taking away all these 95% of the microglia, except now the animals are resistant to cognitive loss caused by radiation, surgery, or traumatic brain injury, right? So somehow or other, those microglia in your brain are actually causing you to be damaged. So obviously one type of therapy would be to actually reduce the microglia in, say, patients before they're going in for surgery. That might reduce postoperative cognitive decline. Third area, which is really quite amazing, you probably have all heard, because it's been even in The Economist, about putting young and old mice together. The old mice get young again. The young mice also get old, but we'll forget about that. So the young mice get, the old mice get even better cognitive powers. We know what's going on with that, right? It's turning out there are progenitor neurons in your hippocampus, the part that gets lost in Alzheimer's. Those progenitor cells lose their ability to divide as we get older. The young blood is actually making them able to divide again. So now Saul Vieda, who's been doing this in QB3, is now working with Andrew Brack to try and see, can we find out what it is in the young blood that's actually making the brains get younger again by using these quiescence assays. The final thing is a complete surprise. We have this very obscure, not obscure, some semi-obscure biological process called the integrated stress response. When you get stressed in all sorts of different ways, infection, starvation, trauma, and so on, your body shuts off most of the translation of proteins. It's not transcription, it's translational control. You don't make proteins, except for a subset. It's like a survival subset that keeps you going when you have these traumas. So you've got these survival proteins that are switched on during the integrated stress response. What happened is that when you look at this integrated stress response, it seems to stay on as we get older, right? So as you get older, it's as though we're still stressed all the time, right, by this molecular mechanism. You can look at it by phosphorylation of a GTPase. It's very easy to do. So, and also that stress response is on in Alzheimer's. Now, the surprising result that got us going on this is there's a drug which resets the integrated stress response. It turns it off again. If you give it to normal animals, you get a tiny, tiny little bit of change in cognition, just a little bit above the noise. However, if you give this drug, which we're developing with Calico, to patients who have, or not patients, I haven't got there yet, sorry, 2 mice who have actually had traumatic brain injury or are old, and the old stuff hasn't been published yet, you get tremendous cognitive improvement, right? So somehow or other, we can switching off this integrated stress response restores our brains. So here's 4 different new ways of thinking about how cognition is impaired as we get older. Each one of those are potential therapies for coming in and approaching Alzheimer's. Now, we've been able to do this by bringing together these people in this network. Now, let me just say, our network doesn't just stop by networking academics together. We go beyond that. You know, I say I'm an entrepreneur. I'm a general partner on 2 venture funds, university-associated venture funds. I'm not paid, so it's not illegal. I'm also a general partner on an incubators. We have about 80 startup companies in an incubator. So when we go say we want academia to network, it's not just to network academic scientists together, but to network them through incubators and venture funds so we can deliver benefits to our customers, which are in fact the patients. So let me then end by concluding that I think that academia, if we want to get faster cures, academia has got to change the way they do it. They need more people who are devoted to networking across disciplines than focusing within their disciplines. That if you do that, I think we've shown in these preliminary results that if you do that and create these pop-up institutes, you can really accelerate the way you come to getting cures for disease. Thank you very much.